working mostly on the proposals and refining your proposal, talking to Carl and Wei and me. I'll be traveling the next few days, but I'll be available next week. So hopefully by end of the week, we'll give you some level of feedback. Okay, so it's kind of an iterative process. In the next couple lectures, while you're working on the merge, I think we're still working on the merge lab, right?
Not. We are waiting for merge to finish.
What?
Yeah.
Oh, so merge has not done it? Okay. Okay. Yeah. So so you will be working on the merge lab very soon. On the other hand, we're going to give you give a couple lectures on what I call the advanced topics. So these are the topics that are built on advanced GPU features that are quite new. And some of these features are implemented probably not the best possible way, but it will take some time to mature. On the other hand, it's always good to think about how the algorithms can evolve as the hardware is being improved, so that by the time that the new hardware, really start to perform in one of the generations, then your code is ready to go. So usually this is what it takes for us to be able to go ahead of everyone else and have very impressive results by the time the hardware starts to really perform. If you wait until the hardware becomes good enough and then develop the method and then so on, it will be too late, right? And so these things take time. This is the reason why historically most of the software that are not even, the development in the software and algorithms did not even happen, start until the hardware, is several generations into these features. And then, so it takes a long, long time for these features to be used, in the history. So, from a research point of view, we really should break that kind of long dependent cycle and then, develop some of these algorithms, ahead of the hardware curve. So today I'm going to talk a little bit about unified memory, and then how the heterogeneous computing collaborative algorithms can benefit or build on this kind of unified memory. So we're going to learn about the collaborative algorithm patterns based on data partitioning and task partitioning. So for data partitioning, we're going to show a few examples and how you can partition the data. And for task partitioning, we have coarse-grained partitioning and fine-grained partitioning. The coarse-grained partitioning, we're going to use breadth-first search as an example. And then the fine-grained task partitioning, I think we're going to be using the RAMSAC example. So not quite Pascal unified memory. So let's take a little review of what we have been talking about so far. So in a typical CUDA code that you write today, we mostly use the CUDA mem copy for data transfer. And so basically we have a GPU kernel that we like to launch, and then we use the CUDA malloc to allocate the output and the input. So the input will be copied with the CUDA main copy, and the output will eventually be copied back from the GPU from the device into the host memory. And the kernel is usually, the launch of the kernel is asynchronous, so the launch will come back right away. And then, so you can, if you want to make sure that your output is ready, you need to do a CUDA device synchronization to make sure that everything is going to be ready for this. And in some cases, you can eliminate synchronization simply because they belong in the same stream. But in general, it's safer, to do the synchronization before you want to actually use the data or copy the data, and just to so that you don't end up with some kind of strange behavior. So started about I would say started in the Pascal generation. The GPU started to have unified memory that can actually the memory can be declared to be for both CPU and GPU. Okay, and so if you have a data structure that you clear to be used by both CPU and GPU, the hardware will manage the data transfer or some kind of coherence or some kind of consistency in order for you to be for both the host and device to be able to access the data, and there will be some properties maintained. So the mechanism that you can do this in CUDA is CUDA malloc managed. So let's say we declare a particular data structure to be CUDA malloc managed and with certain size, and then that particular allocation becomes a unified memory object. And so if the CPU uses it, the CPU will be able to read right into it, and the GPU uses it, GPU can also read right into it. Just like any other shared memory, there will be some kind of consistency model problem. That is, when the CPU writes into it, and then the GPU try to read it, it may or may not give you the most up-to-date result, right? Which is the case in any of the shared memory programming models. So you need to do some synchronization to be able to make sure that you get to the latest version of it. So there are synchronization primitives that that are supported. So in this case, it's the atomic operations based on the unified memory objects. So you can declare a memory location, and then both CPU and GPU can use atomic operations on those. And then the atomic operations will always be serialized between CPU and GPU. And also, if you need to have some kind of synchronous, some kind of coherence, consistency, you can just use atomic operation to write into the location, and it's guaranteed to be reflected to the other side. Whereas if you just do a regular read or write, it will not necessarily reflect to the other side. Okay, and the implementation of unified memory in Pascal hardware is not great. Okay, and the implementation is actually a page fault based approach. And basically, if let's say after the device declares a CUDA malloc managed, the data is going to be residing on the CPU. And then if the GPU kernel go and access that data, the GPU kernel is going to cause a page fault on the GPU, and then the device driver is going to move the data over to the GPU, and then the GPU can do the update. And then if the CPU need to access the data, the CPU will trigger a page fault and grab the data from the page fault handler will grab it from the CPU, and then so back and forth. So if you have a situation where the CPU does a kind of atomic operation and the GPU does atomic operation, and they just kind of pounding on that object back and forth, it's not just they'll be serialized with each other. You actually will have the data transferred back and forth, and it's transferred at a page granularity. So it's not just the particular location that you're trying to do atomic operation now will be transferred. It's also the entire page that is surrounding that whole that variable going to be transferred back and forth. And so this is what we call the traffic magnification. So because of the way these things are designed, even though you're thinking about CPU writing some data into the location, GPU writing some data to the location, when you measure the traffic, it will be the page level data that gets kind of transferred back and forth, and each one is something like a 4K byte. So you will see a lot more traffic than you expect, on the bus, if you measure these things. So it's not the greatest implementation. However, these things will evolve and they will become better and better. Part of the reason why the implementation is so bad is because the CPU and the GPUs are produced by different manufacturers. Okay, so let's say x86 chip is designed by Intel or AMD, right? So even though NVIDIA has the atomic operation and has the unified memory support, allowing these processors to be able to write directly into each other's memory requires each manufacturer to agree on some kind of protocol or some kind of way to coordinate that activity. So if these two companies don't get along, then you go through the least cooperative approach, which is going through the software, and that's the page fault handler. Okay, so many of these things are not strictly technical. These things have to do with company boundaries and whether the CEOs like each other at the moment. Okay, and we see these things again and again. So for example, if you look at the x86 world, none of these, the x86 based machines use NVLink, right? And that's because the Intel and AMD CEOs don't like the NVIDIA CEO. Whereas the IBM machines, Power 8 and Power 9 machines have NVLink, between the CPU and the GPU. It's because the IBM CEO Ginny and the NVIDIA CPU Jensen, like each other for the moment. Okay, so these things, when we teach these things in classes and then write papers, we look at technical feasibility. We look at what are the easy problems and hard problems to solve from the technical sense. But when you go to industry, you have these CPUs. Rather than talking about CPUs, you talk about CEOs. So there's kind of a little transition going on here, right? Okay, so for the for the unified memory, one of the important logical consequences of the unified memory is that once you declare a variable or a data structure to be in the unified memory using CUDA malloc managed, then logically you can treat it as a memory that you can access from both sides, from the CPU side, from the GPU side, and that allows us to begin to think about something I would say more interesting and actually some quite useful patterns of computation that the CPU and GPU can be both engaged in the computation. So that's what we call the heterogeneous collaborative patterns. Heterogeneous means CPU and GPU, and collaborative means that they're actually doing something with together in an overlap way, in a kind of a simultaneous way. So, we're going to to look at some case studies using these CPUs and GPUs, and because the kernel launches are asynchronous, whenever you launch a kernel, the GPU will be going off doing certain work, and because the kernel launch is asynchronous, the CPU will the launch will return from the CPU point of view. So this is what we call the asynchronous, from the host side versus asynchronous from the device side. And so from the host side, the kernel is asynchronous, right? The kernel will be executing, and then the CPU can continue to work on some things here. So you have, CUDA you have the CUDA, you can do the kernel, and then you can do the CPU. You have the CPU to do some work, and then eventually you do a CUDA device synchronize to make sure that the CPU and GPU have both completed their works, and then you do the CUDA main copy to copy back. This is the traditional CUDA. This is not using managed memory. This is just the tradition how you can overlap some activity between the CPU and the GPU. However, if you look at this kind of, the CPU can do things here, typically this piece of code would not try to touch what the GPU is working on. Okay, so GPU will be working on some parts of data, so some kind of data, and the CPU will continue to try to do some work, maybe prepare for the next kernel launch or do something else, and then you synchronize, and then you copy the data back, right? So with the Pascal and the unified memory and all the next generation such as VOTA, we can begin to have a interesting fine-grained collaboration based on the reading, writing of the shared memory as well as atomic operation. So, for example, we can have a CUDA malloc managed input, and then CUDA malloc managed output, and then you launch you launch this kernel. So you're still doing you still launch the kernel is still asynchronous, but then you can come down and then you can begin to actually write into maybe some part of the output. The CPU can actually go and write into part of the output. So this will allow you to be able, for the CPU to be able to do part of the work that the GPU could be doing. So that, let's say if you take a whole array and then you partition, you kind of cut, let's say 80% of the array, and then say GPU do this part, generate the output for these 80% of the locations. But then CPU can still, CPU still has some substantial computing power, right? So the CPU can do the rest 20%, right? So they can write into the same data structure. So this is different from the OpenCL, the OpenCL shared memory model, because the earlier OpenCL shared memory model, if you have an object that is that is being written by one device, and if you try to write into part of that other device, you can actually get a trap, and then it would cause an exception. So OpenCL eventually tried to fix it in 2.0 and so on, but because of the industry, the standard process, they never quite get these things quite ready to be used. So this is the kind of another very interesting phenomena in industry. Basically, ideally, you want to have all the companies come together and define a standard that everyone implements so that the software, hardware can be compatible with each other, right? So OpenCL is an example where multiple companies came together and then they all agree on the standard and they implement the software, and the software can be run across vendor boundaries, in a seamless way. However, if you consider CUDA, CUDA is not an industry standard. CUDA is a proprietary, specification, and that proprietary specification is only supported by NVIDIA, right? So, so if someone else wants to develop a CUDA system, let's say CUDA system or CODA system, and that would not be compatible with the NVIDIA hardware. So if you write code for that thing, it would not be guaranteed to run on the NVIDIA system. So theoretically, you want to have all these things to be standardized, and so that the industry, the software industry can just develop for one, and then it will be run on all the hardware implementations. The problem is, whenever you have a group of companies sitting on the table trying to agree on something, it's never easy. So that's why you'll have extremely slow progress for OpenCL in the history. In fact, looking back, I see probably the progress of OpenCL is at the rate of about 1/4 of CUDA, right? And because everyone requires an agreement. If any of the company on that table does not agree, they cannot move forward. So they will be kind of trapped in the process. So here, when we start to to look at the unified memory from Pascal generation and on, we see that the CPU can now actually write in let's say copy use the input to do some computation and then write into the output. So this is just an illustration. So just assign input to the output, and so you can generate part of the output as the GPU is generating some of the output as well. Or you can do a fetch and add, which is a atomic operation on this data, on this location. So you can do the atomic operation on part of the data structure, and both sides can actually do this do the atomic operation on the same location, and they will be correctly serialized with each other, right? Okay. So what are the tasks in these collaborative algorithms? So we're going to be talking about tasks quite a bit. So let's make sure that we nail down what tasks mean. These things are just the kind of abstractions of the code in the kernel. Okay, so if you look at a kernel, a piece of kernel code, you will see sections of code. So let's just say that this is the first section, second section, third section, and then because the kernel program is being executed by multiple threads, right? So each thread will be executing its own copy of the kernel code. So we illustrate that by having these threads to each have these sections of the kernel code. So the first part, the second part, and the third part may have different nature. Okay, the first part may be doing some kind of computation, and then the second part may be doing something else. So for example, if you look at the merge, right? We talk about the kernel being, the kernel will do, you have multiple steps, right? And then we do the memory search, for example, in one of the steps, right? So those are the things that that are being illustrated with these different shapes. And so we may have the first kernel executed by multiple threads, and then generate some result, and then we may launch another kernel to do to take over. So for example, in the scan in 408, we actually launch multiple kernels, right? Or the kind of the convolution-based color, the sort of the histogram equalization MP with did multiple kernels. So this will be another kernel that we could be invoking, and that kernel will have each thread to execute the kernel code, and these are the different sections of the kernel. So we will refer to things like these shapes as fine-grained subtasks. Okay, and then what the entire kernel does is a coarse-grained task. Okay, and so we will say this whole thing is a kind of a coarse-grained task, and then we have each one will be a fine-grained task because it's done by one of the threads, and then each of these little things is the fine-grained subtask being performed by a thread, right? So that's we're going to be using these terms in that sense. Coarse-grained tasks, coarse-grained task, fine-grained task, and then fine-grained subtask. Okay, so each of these tasks will be processing data. So we're going to be using color to illustrate to indicate some kind of data partitioning. So for example, let's say if we're doing something like a vector addition, then we will have some threads processing, let's say one thread block to process a section, another thread block to process section. Or in the collaborative method, we could have CPU to process a section of the data, and the GPU will process a bigger section of the data, right? So we'll have a coarse-grained task being executed by the CPU, and then a coarse-grained task being executed by the GPU, right? So we can come down here. The data partitioning for the second kernel may be different from the first kernel, right? So if we look at the execution flow of these things, we could have basically the CPU will be executing part of the first task and part of the second task, and the GPU could be processing part of the first task and then a part of the second graph. So we can, that was the data partitioning. So we can just say, okay, these tasks are going to be executed either on CPU or GPU. It's just that we associate or assign different sections of the data to each one, right? So then that's a pretty straightforward, a kind of work, work assignment. So we take portion of the work and give it to the CPU, portion of work to the GPU, but they're executing the same logic code. It's just that the CPU and GPU will be generating different parts of the output. But you can also have task level partitioning. So you can have coarse-grained partitioning, meaning that you can have one executing an entire task, and then the one executing a different task, and then the data gets delivered from the first task to the second task. Or you can do the fine-grained here. The fine-grained partitioning means that the CPU is you take a task, and then you take some of the fine-grained subtasks and assign to one of them, and then the rest of the subtasks assigned to the other one. Usually this is because this section of code is better suited for a particular type of hardware, let's say for the CPU. And then this section is better suited for execution by the GPU, right? So, instead of executing a single kernel on the GPU with all these, this part may suffer, right? It may not have enough parallelism. You may be testing for one thread, using one thread in each thread block to do this. So you could just say CPU execute this part, and then as each of the data comes out of the CPU, it gets delivered to the different GPU threads. And the GPU threads will be picking up the data as the CPU delivers them. So this is why it's called fine-grained, because the data is going to be delivered from the CPU to the GPU on a fine-grained basis, and then GPU threads will be picking up the data from those fine-grained channels. And then typically they're queues. But
internally, it's still using a paging system, right?
Yes, internally, that's a great question. So even though the CPU, it thinks that is writing, let's say, this piece of data to the queue and this piece of data to the queue, but underlying that is actually just writing into all these locations in these pages. And then as soon as the GPU start to pick up the data, the page will be actually brought to the GPU side. So there could be multiple pages even, right?
But wouldn't that happening memory transfers be expensive?
Yes.
Overriding
Yeah. Yeah. The memory transfer can be expensive, and so that's why I'm saying that this generation of implementation is definitely not the best, right? These are just inexpensive implementations as far as the CEOs of both companies are allowed. The way they get along, maybe this is as far as you can go, but then in the future generation, these companies will do better. For example, I'll show you a couple results from the ARM processor on some of these more embedded versions. So because now the CPU and the GPU are now under the same design team from the same company, the implementation is actually better. So these things can evolve. Yes.
So there are 2 points. The first is like you mentioned this unified memory. Like, does it utilize the caches on the CPU, like the L1 and the L2 caches?
Yes.
It does.
There's no reason why it will not use the CPU L1, L2 cache. So just like any other I/O, anything, when you transfer data from CPU to GPU, so basically, these things are in this sort of transparent to the CPU hardware. So if the CPU has some data in the cache, and some piece of the page in the cache and so on, just like any other I/O or communication, it needs to be able to either flush the cache so that the DMA can just do the job, or in some cases the DMA can access the cache through the cache coherence. So there are also transfer the drivers that can actually say, I'm doing the DMA, but I know some of the data is going to be from the cache. So if the hardware supports that, then the cache will intervene during the DMA and say, okay, I have the cache.
Right. So the second question was that, like you mentioned, that in case of a kernel launch, there are some parts that you want that the CPU to execute out of that. So when the CPUs, for example, so there's like a single-threaded part of the code that's better on the CPU. So the GPU would at that time wait and so it will like wait for and check that.
Exactly. So that's exactly the function of the atomic operation. So basically, the method for the GPU to wait is by having a flag that is that can be set by the CPU and then read by the GPU, and both of them are going to be using atomic operation. One to set the flag, one to test the flag.
So in the atomic operations that we have seen, like our atomic add and subtract, so if there are like multiple instructions, then do we have like some locking mechanism or something like that?
You can implement your own lock with the atomic operation, but it's not the kind of the more traditional lock and lock. You need to use the FET.
Test and set of Titanium.
Exactly. To implement the locks. Okay. So where are we? Okay. So the way to think about it is that you have all these kind of subtasks running on the CPU. So the CPU is actually running maybe in terms of iteration or something, and then it's going to they're going to be generating these fine-grained outcome, and they will be passed to the GPU through this this channel, and this channel is like Q. So back to the paging question. If we if the algorithm is designed properly, the CPU will be generating essentially you will be writing a lot of data into the queue. So hopefully each transfer is going to be it's going to involve a large number of the data in that page, rather than every time you write something the GPU pulls something, and that will be a disaster, right? So there are some tiny issues that that will make the page transfer more efficient when you design these algorithms. So the coarse grain task, partitioning is a little bit different. So the coarse grain partitioning means that that the CPU will generate, will execute an entire task, coarse grain task, and generate some kind of data, and then the data will be transferred to the GPU, and the GPU will take up that the data and execute an entire task. So in this case, you can do a more global synchronization. So basically, the CPU will complete this task and generate all the data, and then signal the GPU, and the GPU will just pick up all the pages, right, that contain the data, and so the synchronization can be done less frequently, and then the GPU will say, okay, once the GPU gets the signal, the GPU will perform the operation. However, so that's the benefit of this kind of coarse grain. But the trouble is that when you have this kind of coarse grain partitioning, you lose the overlap between the CPU and the GPU. So because the GPU is going to be waiting for the CPU to finish the entire task, there's nothing that will be executing while the CPU is generating the data. Whereas in the previous case, because the GPU can pick up part of the data during that first phase execution, so the CPU can actually, while the CPU is executing through these subtasks, the GPU can actually have some parts that are active, right? So this allows you to do better overlapping, right? Yes.
So one point is a little off topic, but does the GPU have some like hardware transactional memory? If yes, or why? And
no, this kind of a research. In fact, there are several transaction memory for GPU kind of thing, in the literature, but so far, they're not practical. Okay. Yeah. Maybe in the future. Yep. So these are the task, partitioning. So the only reason why this makes sense is when CPU can execute this much faster than GPU, and GPU can execute this part much faster than CPU. So even though there's no overlap in between, no overlap between the CPU and GPU, it's just that each of these two tasks can now be executed by the device that truly fits or matches that task. And then you can do much faster. So let's say if this task, CPU is 5 times faster than the GPU, and this one, the GPU is 10 times faster than the CPU. So even though they don't overlap, by using a faster device on each side, overall you get much faster execution. So it's about speeding up each individual task enough with a better match, rather than trying to do the overlap, collaboration, and simultaneous utilization of the hardware. Whereas the data partitioning is almost always about overlapping the execution and utilizing the resources. Does that make sense? Okay. So in many of the embedded systems, for FPGAs, it's exactly the same thing. So you have fine-grained collaboration and coarse-grained collaboration between the CPU and the GPU, FPGA. And usually it's because the FPGA are specifically configured to do certain bit-level tasks much faster than the CPU. So then it's worthwhile to have the data transferred to the FPGA, do the operation, and the transfer back to the CPU is still much faster than if the CPU goes through the process itself. Right? Okay, so let's look at a few interesting examples. Hopefully interesting. So histogram. Histogram is squarely a data partitioning kind of situation. So this is the when you do the let's say the image equalization. So when you do the equalization, you need to do the histogram on the the intensity of the image. So you can have this GPU to do a big chunk of the image, and the CPU to do a smaller chunk of the image, depending on the relative compute speed, right, of the two, right? So then you can have the CPU cores. CPU also has multiple cores. GPUs have multiple SMs, streaming multiprocessors. And so if you don't have unified memory, the way to do it is to have private histogram, right? So you have a private histogram for the GPU, private histogram for the CPU, and after you're done, you do the merge, right? You take both histograms and merge that into the final copy, right? So that's the sort of the non-unified memory approach. So this is kind of, you launch the CPU, you launch the GPU, and then you malloc on the GPU, you have alloc on the CPU, and then you launch current, you do this, and then you use the CPU thread to you copy the data back, and you use the CPU threads to do the merge. So with the Pascal and Volta atomic operations, then you can do a single, you can do a single histogram, and you can have the CPUs to do the atomic operations, and GPUs also to do the atomic operations on the same, managed, right? The CUDA, MATLAB managed object. So this is going to be the histogram, sort of the common histogram. And this common histogram is going to be accessed through atomic operations on both sides, from both sides, right? So this goes into a very important question, the question that you were asking. So let's say if I start to have a situation where the CPU and the GPU they really just take turns to hit this data structure with atomic operations, then the data will be transferred back and forth, right? And that's going to be bad, right? So it is going to be a trade-off between how much you're willing to spend after the computation to merge the data structure versus the intermediate data transfers that happen when you execute the histogram itself, right? So that's exactly the trade-off, right? Whether you're doing data transfer at the end and then merge the two, take time to merge the two, or you want to use this kind of stuff. So if you have in general, if the access to a data structure is sparse in some way, or is every time you access something is repetitive, and then before the other party will do something, then this kind of arrangement makes sense. But if you truly have just interleaved access by the CPU and GPU, and timing-wise and location-wise, then this thing can be very slow, right? Okay, but it doesn't mean that in the future this is going to be the case. You can, in the future, we can easily have a situation where the hardware can just essentially the atomic operation can just reach into the other side, right? So that you can just do the atomic operation on one of the sides rather than moving the data back and forth, right? So these they already have some the implementation on the IBM machines that you can lock some of the locations on one of the sides, right? So they're not that far away from being able to say, okay, one of the devices will just reach into the other side. In this case, it should be probably the CPU, because the GPU is going to be pounding on the data structure much faster than the CPU, right? The GPU is going to be doing the bulk of the work. So the CPU will just occasionally reach in and do the atomic operation, right? So that would be make perfect sense. I predict that there will be hardware like that, in the future, quite in the near future. So that's histogram, and then the Bezier surface is just a kind of a Bezier generalization of Bezier curve. So basically, remember that Bezier curve that we talked about in the dynamic refinement, and so each curve is really drawn by 4 control points for a second order Bezier curve. So you can have these higher order higher and higher order curves. And here for a surface, it's just a bilinear interpolation, right? So instead of having just one interpolation variable for one dimension, you can have both dimensions, and then you can have a linear interpolation between the 2 dimensions and map out the surface, right? So out of 4 by the n by n control points. So the higher the order, the larger the n, right? So if you have a strictly linear one, then you only need to have 2 control points, and then you just do a linear interpolation. And then if you have 3, you can do the second order. If you have 4, you can do a higher order, right? So that gives you all the third order interpolation. So this is basically what it is. So you have all these control points, and then these control points are going to be weighed by the bilinear variables, and each linear variable is either a u or v. It's essentially it's x and y, right? And then you can do the interpolation of 1 minus u and then ui, and this is that the polynomial interpolation formula. So when you calculate these surfaces, it is quite expensive. So instead of doing a pre-assignment of a particular part into the CPU or GPU, when you have a heavier computation compared to, let's say, histogram. Histogram is a very, very light computation. You take the value, you find you find the bucket, and then you go and increment that bin, right? The bucket or bin, and that's very, very little. Whereas here, for every set of control points, you're going to do the fairly heavy interpolation, calculation, right? For let's say for that 4x4. Net for the higher level, the third level Bezier surface. So then you can actually just take tiles of control points, and then dynamically determine a CPU or GPU will pick up a tile of control points, because every tile that you spend the overhead to grab and distribute between the CPU and GPU can actually, the overhead is small compared to the real computation that needs to be done for that tile. So this is the reason why, when people work on these dynamic, scheduling, load balancing mechanisms, these things all break down if you start to use them on very lightweight computation, right? But if you have this heavy computation that you need to make on all these data points, then the dynamic parallelism can make sense. So the CPU and the GPU would just kind of, they can just pick up tiles of inputs, and then some of the tiles will be done by the CPU, some of the tiles will be done by the GPU, and then you can actually have you can have essentially assign a percentage of tile, a percentage of the tiles to this, to the CPU or GPU. So in this case, the sweet spot is that we assign 20%. So about 20% of the it's not percentage. This is just portion of the tiles assigned to the GPU, to the CPU. So 20% on the CPU and 80% on the GPU, this is the sweet spot. And then if you assign too much to the CPU, because CPU is slow, right? So it's going to, it's going to, be longer and longer. But if you assign too much to the GPU, then CPU is idle, so that you lose a little bit, and you assign more and more to the GPU. So in this kind of case, if we have a system without the unified memory, we will be doing basically a CUDA main copy to the GPU, and then we would allocate the space, and then we launch the CPU threads, we launch the GPU threads, and then eventually we would do the thread join, and then we do the device synchronization. And if you do this kind of model, it's very hard to implement a dynamic load balancing scheme. Okay, and then you can just essentially statically determine which part goes to the CPU, which part goes to the GPU, and then you let it go. Okay, and then you copy back, and then just kind of merge them together. But if you have unified memory, then you can launch the launch the CPU threads and the GPU threads, and you don't need to pre-copy, and then they can just come and pick their portions of the tiles and along the way, and then they can be done with it. So that's that gives you the dynamic. Instead of having a static partition, you can have them to take turn, the finish, and then as soon as they finish something, they come and pick up the tile. So you will see, some of these tiles will go to CPU, some of that go to GPU along the way, right? And then you'll be done with it. And this gives you a lot better load balancing in general. And so there are only a few of these real challenges in parallel computing, whether it's GPU, whether it's clusters. So for example, the Sanjay Kalei in CS, right? He spent his lifetime building Charm++. And one of the biggest things that Charm++ supports is that dynamic load balance, right? And it's so important a problem that someone spends 10, 20 years, okay, building systems trying to solve that problem, right? So that's sometimes how hard these problems can be. And it's not surprising that when GPUs try to enable these kind of things, it may take generations of hardware before they can get it right. The next one is actually a somewhat important pattern because I did not talk about this particular pattern in 508, and that's one thing that we may change in the future. But this is the part that we talk about it. Hopefully it's sufficient. If not, then we'll expand it into a full lecture on its own. So there's some interesting computation patterns that are not very not very suitable for a simple vector execution or simple Bach synchronous execution. So this is one of them. So let's say if you have a matrix like this, and you want to be able to add a column. Okay, you want to add a column to this matrix. Okay, so the logical way of looking at it is that you're going to be adding one more column to the logical representation, right? And then you're done with it. But the problem is that's the logical way of looking at it, right? So in reality, it's actually not. It's about inserting an empty one here and move everyone down by one location. And then add another empty one here and then move everyone down by two locations, right? So this is what we call a data shifting problem. It actually happens quite a bit in different contexts. So matrix tensor padding for the different inferences is actually one of the the frequently occurring computation in, let's say, some of the neural net implementations and so on. So when you implement this kind of padding, we can have the CPU and the GPU to collaborate, and then when you assign about 30% or so of the computation to the CPU and 70% of the computation to the GPU, you get a sweet spot. However, even on this, let's say even if we're just writing GPU code, there's a very important problem. The problem is, let's say we want to assign each of these to a thread block. Okay, so each row to a thread block. So the thread block will be responsible for moving all those data elements in the row, right? So let's say thread block 0 will move this row, thread block 1 will move this row. So there are two ways you can do this. One is you can do out of place movement. So out of place movement says, I'm going to move it into a different area. So I pre-calculate that these ones will need to go to a particular set of locations, and these will go to another particular location. So then there's no dependence. And that's where the Bach synchronization, synchronous or vector execution can work. And that will be very similar to the merge pattern, where each thread or each thread block will go and look for the input, right? And then identify the output section and then just do the execution. However, in many applications, that out of place data movement is not acceptable because there may not be enough memory for you to do that, right? So that's when if you need to do in place the data movement, then there's a problem. The problem is, remember the first one is not going to move, and all the row elements in the second row will move by one location, right? And all the elements in the third row will move by two locations. So if we move any of those rows too early, it will overwrite, right? It will overwrite the locations, down here. So you need to start with this, the last row, move it by enough element locations, get out of the way, and then the next one can come in and then move by one fewer location, and then the next one can come in, so that but you need to make sure that these later rows get out of the way. So there's a kind of a synchronization going on or dependence. So what we do is we actually create, we use these flags, okay, we use these flags, and then we take we have the thread blocks or threads to basically, move the data. So, in this case, the CPU is responsible for some of them, the GPU is going to be responsible for some. And then, you will take the CPU to, CPU and GPU will make these movements. And then the CPU will say, okay, I'm going to copy enough of the data, right? Enough the data to this, and then the GPU will need to wait until the CPU has secured enough of the data into this location before it will write into the original location of the last row. So every time someone finishes the movement in one of the later rows, it will signal and say, now you can move, right? And then you're not going to trample me anymore. So then you enable more and more. This is what we call the domino algorithm, because you have these dominoes ready to go, and then once you're done with the last row, you flip it, and then the next row, the next row, the next row. You just enable more and more of the rows. And if you signal well enough, then you can actually get some substantial overlap in your execution. So this is, this kind of pattern also happens quite a bit in things like string compaction. So if you have these kind of if you deleted some data from a data structure, and then you want to do a compaction, you want to eliminate those, eliminate the data from the data structure, then you need to move the data, right? You need to move the data forward to to squeeze away all these deleted elements. So or zero elements or dummy elements. So when you do this, you need to make sure that you have moved all these elements out of the way before before you can move these elements into their previous location. So again, it's a domino kind of algorithm. And you can actually prove that the fastest implementation of scan is also a domino algorithm. Okay? And that's a very sophisticated method. It would allow you not to have to launch multiple kernels, right? So those, that's why these algorithms tend to have these patterns. So if I have enough time, I'm actually going to add a lecture on how the major types of domino algorithms work. But for now, the important part for this part of the lecture is that we're going to be using atomic operations, right, for some of the thread blocks to signal the next, for a thread block to signal the next thread block and say, now you can go. And then it will signal the next thread blocks and you can go. But if you begin to have CPU and GPU to collaborate, you also need to make sure that there's ability for the CPU to signal the GPU threads or thread blocks, say now you can go, right? So that's the kind of the collaboration support that we need. So there are coarse-grained task partition. So this is actually one of the high-performance breadth-first search. We already talked about breadth-first search, right? And so one of the problems with breadth-first search is that the profile of the frontier size, right, grows, and then the tapers, right? So we talk about the small size kernels, right, and the big the bigger kernels. So we launch different kinds of kernels in order to capture the different size regime, so that we can eliminate the kernel launch overhead for some of for the initial section, and then we can launch big kernels when the frontier gets big enough. However, we can actually use the atomic-based synchronization and use what we call the persistent thread blocks to be able to achieve similar effect, not all the benefits, but similar effect with simpler code. Okay, so that we don't have to launch two kernels and switch between the kernels. So basically, we'll have a single kernel, and the kernel will would have persistent thread blocks, and the persistent thread block needs to be no more than the number of SMs times the maximum blocks per SM. That is, none of the thread blocks